This is a carbon-S photoemission peak, and it has a characteristic asymmetric shape that is typical of polypropylene and is not dissimilar from the shape seen for polyethylene. Now, the difference between polyethylene and polypropylene is an additional fragment here, which is a CH3 fragment that is bonded with one of these carbon atoms. So in principle, the polypropylene may have shifted peaks as a result of the different chemical state for these two carbon atoms. In the case of polyethylene, we have two carbon atoms that are in entirely equivalent environments within the polymer. Since these carbon atoms are in equivalent chemical states, the justification for additional peaks must be made on the basis of some other phenomena, such as vibrational states. What we would like to do is use the peak model from polyethylene and construct a peak model for the polypropylene that is making use of a similar type of structure that accounts for the asymmetry and also account for some chemical shifts. In an earlier video, a peak model for polyethylene was constructed that involved a sequence of these peaks that were calculated by defining a constant offset representing the vibrational states, and then fixing the full width half maximum, as you can see here in terms of the constraints, and then allowing the peak areas to adjust to accommodate the data. So at this point we have a peak model with a set of peaks that are modeling the asymmetry for polyethylene, and they're defined in terms of 5 different components. So what we're going to do is take a copy of these and move these over to the polypropylene as the basis for constructing 2 peaks that will ultimately fit the 2 different forms of the chemical state of carbon within the polypropylene. Before adding the components from the polyethylene, what we need to do is create a background. So on the regions property page, we need to construct a background that is suitable for the polypropylene, and then going to the components property page, we can paste the components that were copied from the polyethylene. Now these components have been brought through with the constraints that were applied to the polyethylene. So as it stands, we have each and every one of these areas free to adjust when optimized. So we need to correct that for the polypropylene on the basis that we would like to use this particular structure here to represent vibrational states for these carbon atoms. The tool we'll use to organize the constraints for these component peaks is the component index. And this is a parameter that can be used to display components with a specific color, and it's also used to transfer information between component peaks in terms of constraints. And this is exactly what we need to do to take this polyethylene peak structure and create 2 sets of peaks representing 2 different chemical states within polypropylene. The first thing we'll do is create a display of the components based on the component indices. This will help us understand the relationships that we're setting up on the basis of these component indices. So right now we have the component index is set to 0, 1, 2, etc. And so these colors are all different. However, if I set these to a common color, so I say reset, that'll set them all to -1. So they all get displayed now using one color, and it's the default color, but I can now set this to be a specific color by saying set equals 0, and then all component indices with that same index of -1 will be assigned 0. So we now have a different color, and because they all have the same component index, which is reflected in the color, we can now go to the area constraint, and if we say lock as the key word in the area constraint and press return, then all of the components with the same component index are then assigned a constraint in terms of area that is calculated based on the current relationship between these component areas for this sequence of peaks. At this point we've got the full width half maximum, we've got the area, and the position for each of these component peaks all linked to the component in column A. So the only adjustable parameters for this entire set of components are these three parameters here. This means that if I pick up the component and move it corresponding to column A, the entire set move. We also have a common component index of 0. So what I'm going to do is copy the state of these right now, and then I'm going to set the current set of component indices to a different value. I'm setting it equal to 1. So all of these components have identical constraints, but they now have a different component index. And since I copied the set before I adjusted the component index, if I say paste, I now have 10 peaks rather than 5, and as a result I've got two sets with two different component indices. So when I move one set relative to the other, you can now see that we've got two sets of components, each representing different chemical states within this polypropylene. So if I move now these peaks into the peak up for polypropylene and say fit, I end up with my first approximation of the peak model for polypropylene. Polypropylene should have two peaks in the ratio of 2 to 1, and in order to see this when we've got sets of component peaks rather than individual line shapes representing these different states, we need to use the component index to create a table that gathers the information from the different component indices and reports it as a % area. And this particular table is showing us that we do not quite have the ratio of 2 to 1 that we might expect for polypropylene. Despite making use of multiple peaks, we can still introduce constraints to check the relationship between photoemission processes. So for example, here we could say F star 0.5 as the constraint for one set of peaks compared to the other. So F is the controlling peak for one set of the 5 components, and if I press return on this, you can now see that you get the stoichiometry you'd expect, but the residual has worsened as a result. So if I say fit, I then once again return a comparable residual standard deviation, and you can see the residual is showing some signs that it could be improved upon, but we have the correct relationship now by virtue of using a parameter constraint applied to the controlling peak within each of these 5 component peaks representing the photoemission from these two different carbon states. So let's next have a look at the background and just see what is happening down here. I have to close the annotation history, and yes, I can see there is a problem here, so I'm going to adjust my limits, and then we'll say fit again, and we've got an improved residual standard deviation, and we've got a fit that looks plausible for the polypropylene. It's at least consistent with the type of relationship that you would see in Beamson and Briggs polymer database. So let's just do one final thing to illustrate what we have here. Is if we combine these component indices, so we can actually see, let me just turn off the labels, and you can see you've got a pair of asymmetric peaks that would be consistent with the type of shape you see for polyethylene, and they fit in the right proportion for polypropylene.